I'm really excited to be here at our 5th Digital Factory. This is a really great venue to bring together people working across digital design and manufacturing and trying to bring what software can do well to the world of design and manufacturing. And it's really great to go on right after Andrew from Autodesk, because the way I see it, Formlabs has roughly the same mission. Our goal is to make it easier to go from an idea to a real thing. Autodesk works on kind of idea to digital design, and Formlabs goes from digital design to real thing, at least for some subset of manufacturing processes. And for any of you who have made something, designed a product, maybe had a home built or something like that, you've probably been through this cycle where pretty early in that process, you can imagine the thing that you're going to build. You have an idea what it's going to look like, and you even start to sketch out the details, and you'll have a picture of what it is. And that's maybe like 10% of the way through the process. And then comes along really frustrating part of the process where your idea gets cut down by the limitations of what you can make. Things take longer, more expensive. And it really feels like you're grinding through that. But there is a better way. And the software world shows us that that's possible. As Andrew was talking about, if we can have a circular process, we can understand what will come out of the design, what can be made, and we can do that up front and do it in an iterative way. You can build things, design things, build them better, make better products faster. And this is really important. Almost everyone here is working on, in some way involved with building something that is supposed to make our world a better place, whether it's a medical device or a new power generation technology that will help our world be a more sustainable place. We need to make these things, and we need to make them better, faster. And again, we're really inspired by software. Like, here's a picture of what one of the most important and valuable pieces of software, the team and the company that built it in the early days, a couple of people in a room without a lot of resources. And that scale of impact is incredible. Meanwhile, Formlabs, this was our first primitive factory that built a product that was still kind of just a prototype. And this is like the minimum you need to get started. So I'm jealous of what it's like to build software products, and I want making physical things to be a little bit more like that. So we've been working on this since the beginning of the company, and we've made some progress. As you heard earlier, we've shipped 130,000 professional 3D printers. That's more professional 3D printers than any other company in the world. Thank you. But we're still scratching the surface. We make a tiny portion of all the things made in the world, even all the plastic things made in the world. And you might start to ask yourself, why? Doesn't a 3D printer kind of solve that problem of going from a digital design to a real thing? They work. You can throw a design at them and get a part out in a few hours. Well, there's a lot of limitations. And what they generally do well, especially high-resolution 3D printers like we make, is go from that digital design to a shape. But everything in the physical world is a combination of shape and materials. And the performance of everything in the world depends on both its shape and materials. And the materials in 3D printing aren't good enough yet. So if you look at, just to go a little deeper on this, like things that exist in the world like a beam or a wire, what is their performance determined by? If you write down the simple equations that drive them, they are actually literally a product of shape and material. And you can go through everything in the world and look at it from that perspective. And the way engineering technology development happens today is these two areas are split up into different subdisciplines. And we have shape engineers, more commonly known as mechanical engineers, or maybe architects, and material scientists. And they work in their silos separately. And they'll typically iterate on this equation kind of independently. A material scientist might try to develop a new material that works within a given shaping process, or a mechanical engineer might try to improve the shape of something with given materials. And that works to an extent. You can get steady, incremental, 10% type of progress. But if you want breakthroughs, you have to work on this problem holistically. So I want to go through just a couple examples in history that are, for me, big inspirations and a little bit of what we're trying to capture at Formlabs. And if nothing else, I think interesting to anyone in manufacturing. So the jet engine. Jet engines obviously power airplanes that fly us all around the world. They've made, there's been amazing improvements in air travel over the last few decades. But for me, the most important thing is it's become more accessible, and that's helped to connect our world. And a lot of that has come from improving efficiency of jet engines. Today, they are dramatically more efficient than they were decades ago. How do you improve the efficiency of a jet engine? One of the main limiting factors is how hot it can run at. There's a basic thermodynamic relationship there. The hotter the gas is inside it, the more efficient you can make the engine. And that's a problem because parts of the engine can't take the heat. And there's a specific part of the engine that's the first thing that comes right after the combustion part of the engine. It's called the high-pressure turbine. And the turbine blade in there, so like a few inch long piece of metal, that is one of the key things that sets the performance of the engine. And today, a turbine blade is one of the pinnacles of human technology development. So much work and billions of dollars over decades have gone into improving that thing. A modern turbine blade operates in gas that's more than 100 degrees C hotter than its melting point. So that's like making your engine out of an ice cube that's in an oven. Pretty amazing performance. And to do that, there's been amazing improvements on both shape and materials to get there. Turbine blades have cooling that has got increasingly more and more complex until a modern blade is just perforated with channels, cooling different surfaces, different techniques on different parts of it, and that's incredibly complex manufacturing process. You can try to imagine how do you make something like that out of a piece of metal. And the other half is materials. So the limit, even before you melt a material, is it starts to creep, and the turbine blade's going around really fast under very high loads. So when you bring it close to its melting point, it'll start to stretch. Obviously not something you want happening in your engine. And that creep happens at crystal boundaries in the material. Almost every metal around you is made out of lots of small crystals, which is a great opportunity for that thing to creep. And so over time, people have figured out how to grow longer and bigger crystals. Until today, a jet engine blade is actually made out of a single crystal. That's one of the only places like in technology that we make single crystals. The other would be in microchips. Can't get into here, but there's an amazing thing called the spiral crystal selector you can see at the bottom of the blade that allows only one crystal to end up growing through that part as you freeze it. Really amazing stuff. In a different domain, buildings, especially in a downtown area like this, you'll see a lot of buildings covered in glass. And glass is amazing for making buildings because you can have a light, airy space, especially in an urban environment. There basically weren't glass-covered buildings until the 1950s. And why is that? Glass is old and doesn't seem particularly expensive or special. Well, the key property of glass is, of course, that it's transparent, and that requires a transparent material, but also a nanoscale smooth surface. And you used to get that by casting a sheet of glass and then grinding a surface, labor-intensive, expensive process. Until Sir Alistair Pilkington in around 1950 invented the float glass process. And this is just amazing. You guys should watch some videos of this on YouTube afterwards. The float glass process involves a huge furnace melting hundreds of tons of glass and then casting it down onto a molten river of tin that's like 100 meters long. And so that glass flows out over that river, and because the tin is perfectly smooth, you get a perfectly smooth finished piece of glass, essentially finished piece of glass coming off the end in a continuous process. And that plummeted the cost of glass and let us make huge sheets now that we can cover buildings. So yeah, these are just a few examples that, that I think are a little bit of what we're trying to capture. In fact, at Formlabs, we code name our product developments after people like Pilkington and Bessemer and other people who've changed our world through these shape and material processes. We've been, so 3D printers kind of come with shape, they're strong as shape, but the materials aren't there. And we've been working on that since the beginning. We started years ago with a single general purpose kind of rigid material. And we've built up on that over time, pushing the frontier of different properties like strength and stiffness and impact resistance, and building out this portfolio of materials that lets you cover more and more applications. This is showing our engineering lineup. We have an even wider lineup beyond that, going into biocompatible materials. We have a factory in Ohio where we make these materials, and it's a ISO 13485 facility, class 1 and 2 materials, different materials for special functions like lost wax casting. And I'm proud to say that we have the widest lineup of supported materials on any one 3D printer in the market today. But it's not enough. We still have a small fraction of what's possible in other manufacturing processes and a limited range of properties. And that means that the things that you can 3D print ends up being a small subset of what could benefit from 3D printing. So we've got to push this further. And that's why I'm excited to make a couple announcements today of pushing our materials lineup further. So first up, everything we have today is a polymer. And polymers have a range of properties that go up to maybe 10 gigapascals in stiffness. There are totally other families of materials that can go way further than that. And in fact, we have one with a stiffness that's about 40 times higher, 380 gigapascals, just a completely different regime. And that is an alumina ceramic. So ceramics are amazing materials with a crazy range of capabilities that you don't find with other materials. I'll show you a couple examples here, and these are all with our printed parts. So temperature resistance, this is a filter for molten metal, that white part at the bottom there. Chemical stability, this is a mixing element inside something called piranha etch, which is incredibly corrosive to any sort of organic material. And hardness, here scratching glass. Alumina is actually much, much harder than glass and just short of diamond as one of the hardest materials known to man. So you might be asking, like, why aren't there more ceramics in the world? They have these amazing properties. And there's this concept in ceramics that, in the technical ceramics world, that nobody ever wants to use a ceramic, but sometimes you have to. And that's because it's very difficult to shape. Those amazing properties that it has also mean it's very difficult to shape. It's very high temperature, so it's hard to melt, very hard, so it's hard to cut. And so if you look at typical ceramic parts in the world, these are not ours, they often have fairly simple shapes because you're limited in your ability to shape those materials. But if you look at 3D printed ceramics, you can bring total flexibility in shape to this amazing material. And we're really excited to do that with alumina. Now, to be clear, you can't get a finished ceramic part straight out of a $3,000 printer yet. The process that we run here is a powder ceramic type process. So you print what's called a green part, where you have a powdered ceramic in a polymer binder, Then you go through a debinding and then a sintering step. Sintering, you put it in a furnace and heat it up to close to its melting point where those particles fuse together and densify. But that can all be done with about $10,000 of equipment, and it's not an enormously complex process. So we're excited that we're making ceramic manufacturing and really well-shaped ceramics dramatically more accessible than they ever have been. And one of the things I'm really excited about, we've been beta testing this with different customers, and one of our early users is Bosch. Bosch, obviously diversified, big company making all sorts of stuff, but they make things like spark plugs that have ceramic as a key part of them, and they're actually a very high volume ceramic manufacturer. And Dr. Hartmann from Bosch has this to say: by offering a low-cost production setup, Formlabs opens up a new chapter for the additive manufacturing of ceramics. The Formlabs ecosystem is a perfect choice for organizations looking to directly print ceramic parts. That's awesome to hear from a company that has all of the most advanced capabilities in this field, making parts at high volume, higher end, more expensive 3D printing systems, but they still see the potential of blowing this material wide open and bringing it to more applications. Today, it just doesn't get used where it could get used, and hopefully we're going to change that. Last thing on ceramics, this is the beginning of a new family. The same technology can bring a wider range of ceramics to our printing system. You can have things like zirconia that's used to make knives, or hydroxyapatite that's used for implants going into bone, all possible in this process, and we're eager to keep investing. Love to hear from all of you if there's any specific materials or applications you want us to focus on. So ceramics, they're very stiff at high temperature. You always kind of look for combinations of properties in materials. What if you want low stiffness at high temperature? You need something that's going to be compliant and flexible. Well, the best material in that part of the materials world, the best family, is silicone. And that's our second announcement for today. We are bringing a pure silicone to a high-resolution 3D printing platform. This is a really big deal, and the first time it's been done. Today, almost all the materials that you find on high-resolution 3D printers are based on chemistries like acrylates and epoxies, which are really best suited to make stiff materials. And you can kind of fudge them into making a soft material, but they don't make great soft materials. You really need silicone chemistry to make a great high-performance elastomer. And that's what we've done. So silicones, they also have great chemical resistance, so you can cover them in greases, temperature, performance, wear resistance, so they make seals and gaskets is one really common application. And they've got great lifetime and robustness, so you can repeatedly cycle them and get a really wide range of applications around that. Lots of things in robotics. You can see some sort of grippers, inflatable parts, things like that. But when I think about silicones and what sort of products are around us, one of the best places you'll find them used is in the kitchen. Kitchen environment can actually be pretty demanding. You have acids and alcohols and temperature and wear and sort of a intense environment with a lot of factors. And silicones are often the only thing that can stand up to in something like a spatula or an oven mitt or other applications like that. And there is one company that has really done an amazing job in this space and uses silicone for a lot of their products. And they've been an early beta tester of silicone. So I'd like to, and that company is OXO. So I'd like to invite Mack Mor, principal engineer from OXO, on stage to tell us a little bit more about why silicones are interesting and what OXO does with them.
Thanks, Max. So, hi everyone, my name's Mack, principal engineer at OXO. So we use silicone for lots of our products. We use it for seals, gaskets, food contact surfaces, and even just the whole product itself. So for most of those parts, we use silicone because there is just no other good material option for what we need. It's the best material to use for flexible parts that need to stand up to high temperatures, hold their shape over time, or make a really tight seal. And it also effectively resists chemicals even after very long-term exposure. So one of the most important properties that we look for in silicone is its resistance to stress relaxation. If you handle a part, you'd know it immediately. You'd probably describe it as springiness. So it's the reason a silicone part and a part maybe you printed in Formlabs elastic resin might have the same durometer, but they just feel totally different. The silicone is more resilient. Silicone also has the highest temperature resistance of any non-metal material that we use. It can hold up easily to a saute pan. We make products for use directly in ovens and pressure cookers, and boiling water is no problem at all. Boil silicone all day. So all those unique properties make silicone really, really important for us. But historically, it's been a challenge for us to prototype because we have to cast it or mold it. And for many years, we've casted and molded silicone in molds that we 3D print on Formlabs printers. But this ability now that we have to directly 3D print the silicone itself helps us iterate so much faster. And it's really important to do this iteration because seals and other flexible components are just very difficult and often inefficient to design using analysis alone. So the ability to reduce our iteration time and do more iterations just helps us make products that really work for our customers.
Awesome. Thank you, Mac.
Thanks, Max.
So silicones, as with ceramics, this is a beginning of a totally new family. There's a new chemistry here, and you can do harder, softer, biocompatible, really wide range of applications. We're continuing to work on the family, but again, if you've got specific applications and things you really need 3D printed silicone for, please talk to us. So the last announcement, there's a lot in here. I just want to briefly touch on it, but we realize that while we've made good progress with expanding our kind of first-party, well-supported material lineup, we're still just scratching the surface, and we can't do it alone. We need to bring more high-performance materials to 3D printing faster. And to do that, we need to open up our systems to a much wider variety of people developing materials. And that's why we've got a couple of announcements around an open platform. We're going to have certified materials where we'll have third parties bringing their own materials to our system, but in a way where they're supported and work the same way as our materials. We're going to have an open material license where you can run any material at all on our systems, especially targeted at people who are doing R&D and trying to develop more materials. And then lastly, material settings editor, opening up more parameters in our system so you can tune them. This doesn't mean we're going to put any less work into making our systems work well out of the box, but we know there's always demanding customers who want to take it even further, and we need to give them the tools to do that. So I'm really excited about the announcements we've made today. They bring us one step closer to our vision of the future. We love making things. We love making things that make an impact, a positive impact on the world. And we know that that process is still a frustrating, messy, and slow process. And our goal is to make tools for all of you to be able to do that faster and better and make the things that we need to change our world. I hope all of you will join us on this quest and have a good rest of the show. Thank you.